Thank you.
Thank you. I'm Agnese Zardini. This work deals with the development of a model that estimate the absolute abundance of Aedes albopictus and Aedes aegypti and the potential risk of transmission of different vector-borne diseases in the Americas and Europe. The growing burden of mosquito-borne diseases creates the urgent need to understand their global distribution and the temporal dynamics of the observed epidemics. Several approaches have been developed with this aim. One approach widely used is based on a mechanistic model, which, however, are usually calibrated on local epidemiological or entomological data and may result computationally intensive when applied at large and detailed spatial scales. For these reasons, these approaches are mainly used to investigate only local mosquito population or epidemic dynamics. There are also several models that estimate the habitat suitability of different mosquito species or of vector-borne diseases. However, these approaches usually do not provide any information neither on the seasonal pattern that characterize mosquito population, nor on the expected overall abundance of the vectors or the transmission intensity. The presented approach is based on two assumptions. The first one is that the mosquito relative density depends on the local climate suitability, which we estimated using a logistic regression model. The second assumption is that the increase in the mosquito abundance occurs as a consequence of persisting favorable temperature conditions over a certain period. In particular, we assume that the number of captured mosquitoes can be approximated as a logistic function of the mean temperature recorded over a certain time window. Then, we quantify the absolute abundance of Aedes albopictus and Aedes aegypti by using the available estimates on the flight range and the capture rate. Obtained results were then combined with the population data in order to assess the transmission potential of chikungunya, dengue, and Zika. So, in the first step, we estimate the climate suitability through a logistic regression model applied to presence-absence records available for different US counties and European locations. We considered different explanatory variables that depends on the temperature and the precipitation. As expected, tropical and subtropical areas are estimated to be the most suitable regions for the presence of both mosquito species, and Aedes albopictus shows a wider geographical distribution which extends also to Europe and the temperate areas of the Americas. Then, in the second step, we approximated the number of captured mosquitoes in a given day D with a logistic regression model, as a logistic model of the mean temperature recorded in the W preceding days. The model has therefore the following formulation, where L, K, and T0 are the maximum, the steepness, and the midpoint of the logistic function. The model was calibrated through a MCMC approach based on a large set of entomological data collected across different locations of Italy, US, and Brazil under different trapping conditions. In the model, we assume that K, W, and T0 are site and trap independent, while L was allowed to vary across the different sites. In particular, L was defined as proportional to the estimated climate suitability through a trap-dependent parameter. As you can see, the model is able to well capture the temporal dynamics of the analyzed entomological data. Finally, we estimate the absolute abundance of Aedes albopictus and Aedes aegypti using the available estimates on the flight range and the capture rate. This figure, I'm sorry for, I don't know why the maps are. This figure shows the temporal dynamics of the estimated absolute abundance of Aedes albopictus and Aedes aegypti in the Americas at a spatial resolution of 1 kilometers times 1 kilometers. In the tropical areas, the mosquito population is expected to remain rather than constant during the whole year, while in the temperate areas, the mosquito density is characterized by a strong seasonality. Moreover, we found that the absolute number of Aedes aegypti is estimated to be more than 6 times higher than the absolute number of Aedes albopictus. Also in Europe, the absolute abundance of Aedes albopictus shows a strong seasonality. For example, here in Rome, we estimated that the number of Aedes albopictus ranges between 0 in January to about 600 mosquitoes per hectare at the end of the summer. Obtained results were then combined with population data in order to assess the transmission potential of chikungunya, dengue, and Zika. To this aim, we use a standard formulation in which there are some parameters that are biological, that are disease-specific, and other parameters that are biological parameters of the vectors or of the hosts. This figure shows the temporal dynamics of the estimated transmission potential of dengue and chikungunya. We estimated that these diseases are endemic in many countries of the Central and South Americas, and Aedes aegypti is estimated to be the main vector for the transmission of all these of all the analyzed mosquito-borne diseases, but we estimated that Aedes albopictus may contribute to the spread of chikungunya in large portions of the Americas. The model was validated against historical records of presence of Aedes aegypti in Europe and against an independent dataset of occurrence records of both mosquito species in Europe and the Americas. The estimated climate suitability of Aedes aegypti in Europe is compliant with its historical distribution. And on the other hand, as shown by the table, we estimated a probability of mosquito presence higher than 0.5 in more than 95% of the locations where the mosquitoes were actually observed. Then we also compare the estimated R0 with the distribution of the observed cases. And the areas that we estimated to be at higher risk of infections well reflect the current areas of disease occurrence in Brazil and in US. Finally, we validated the estimated R0 with the estimates provided by previous studies analyzing local outbreaks. For example, The average R0 estimated for Porto Alegre, which is a city in Brazil, is compliant with the reproduction numbers estimated for this location between 2013 and 2017 and 16. Similarly, the estimated transmission potential of chikungunya that we computed for 3 municipalities of Italy are compliant with the results published on outbreaks that occurred in these locations between 2007 and in 2007 and in 2017. So, in conclusion, I have presented an innovative model that provides estimates that allows estimating the overall abundance of Aedes albopictus and Aedes aegypti and the consequence risk of transmission of chikungunya, dengue, and Zika in Europe and the Americas at a high spatial temporal resolution on the basis of only temperature and precipitation records. Moreover, this model provides estimates in areas where entomological data are scarce or unavailable. Of course, this approach has also some limitation. The first one is that it is calibrated on a large set of entomological data that, however, are mainly collected in US. Moreover, to estimate the climate suitability of the Americas, we employed a logistic regression model that were calibrated against data aggregated at the county level. The presented estimates on the absolute abundance of the 2 mosquito species crucially depends on the capture rate. Moreover, in our approach, we do not consider for the progressive expansion and the competition of mosquito species and the control measures put in place to reduce the vector abundance. Finally, the estimates of R0 may not reflect the real risk of disease spread, which depends on a variety of factors such as the human mobility, the level of immunity, and the probability of case importation. Thank you.